Well, I'm sure all of you have seen sci-fi movies that have something mentioned about quantum. But what is it actually, and why do they use it? Well, to put it in very basic terms, quantum subject has a lot to do with things at subatomic scale. While quantum has many study branches, most notably the quantum physics, there are also other ones that are equally important but are often overlooked. One of these being the quantum chemistry. Basically, quantum chemistry deals with the things and the study of matter and its interaction at the smallest scale imaginable in the realm of atoms and subatomic particles. In this field of science, the quantum chemistry, the scientists explore how the atoms and molecules behave, their interaction with one another, and how they transform. By understanding the fundamental processes, we get to know more about the secrets that shape the world around us. At the very heart of quantum chemistry lie the concept of electrons, which are the tiny negatively charged particles that exist in the specific energy levels or shells around the atomic nucleus. These energy levels can be further divided into orbitals, which represents the probability of finding an electron with a specific region around the nucleus. Here, the quantum mechanics come into play as it provides us with the tools that describe and predict the behaviors of the electrons. By applying the principles of the quantum mechanics to the chemical systems, we gain insights into the intricacies of the chemical reactions. All in all, the quantum chemistry helps us to understand why certain reaction occurs, uncovering the building blocks of matter and unraveling the mysteries of the universe. To kickstart it off, we would like to go back to the very beginning, the discovery of the atomic models.
In early Greeks, Democritus contributed to the atomic theory. He implied that the universe consists of an empty space and an almost infinite number of indivisible particles and invisible particles. The mentioned atom is the smallest particle of an element that characterizes the element particles, and they diverge in shapes, sizes, and masses. However, there were no experiments conducted during the early Greeks, but instead early theory were conducted. Later on, Dalton developed the idea of atom from the Greek idea, stating that atom is the smallest particle with different masses and properties. And after Dalton, J.J. Thomson discovered the plum pudding model of atoms from the cathode rays experiment. The electrons were embedded in a uniform sphere of positive charge, like blueberries stuck into a muffin. Rutherford conducted the gopher experiment. He shot some alpha particles at the gopher. He made a new claims about atoms. Electrons were small and negative, therefore, an atom must have a small positive nucleus surrounded by electrons. However, those scientists could not explain what electrons are. Why didn't the electrons drop into the nucleus according to the classical physics? And how is the discrete emission lines produced by excited elements correlated to the internal structure of atom? Bohr models of hydrogen atom were used to explain the radiation spectra of atomic hydrogen. In 1913, he introduced the concept of energy level, spectral lines, and atomic model. Bohr suggested that the electrons move into specific orbitals and quantize energy. Bohr developed his model from Rutherford theory. He stated that a small positively charged nucleus was surrounded by the negatively charged electrons, and the closer to the nucleus, the less energy it has. The Bohr model shows the model of the central nucleus surrounded by protons and neutrons with electrons moving in circular orbits. The closer to the nucleus, the lower energy it has. In order for it to move in a shell, an electron must absorb or release a fixed amount of energy corresponding to the difference in energy between the shells. For example, if electrons absorb energy from a photon, it will become excited and move to a higher energy shell. The lowest energy, most stable arrangement is what atoms, like all other subjects to the rules of physics, choose to adopt. Therefore, electrons fill up lower energy shells closer to the nucleus before moving into a higher energy shells further out. Atoms' electron shells are filled up from the inside out. The one-end shell, which is the one nearest to the nucleus, may accommodate 2 electrons, while the second and third shells can accommodate 8 and 18 electrons respectively. The reactivity of an atom, or propensity to establish chemical interactions with other atoms, depends on the amount of electrons in its outermost shell. The electrons located in the outermost shells are referred to as valence electrons, and this shells is known as the valence shells. In general, when an atom's outermost electron shell is full, it is at its most stable and least reactive. The octet rule states that most biologically significant elements require 8 electrons in their outermost shell in order to be stable.
Quantum numbers are a set of numbers used to describe the position and energy of the electron in an atom. The combination of all quantum numbers is described by a wave function that complies with the Schrödinger equation. They are important because they are used to determine the electron configuration and the probable locations of the electrons. First number is principal quantum number, or n. It is the energy level of an atom. The larger the number n is, the farther away the electrons are from the nucleus. The value n equals 1 is the innermost electron shell, which has the lowest energy state of an electron, also known as the ground state, so therefore n cannot be a negative value. The second number is the angular momentum quantum number, or L. It is the general shape of a given orbital where an electron occupies. Its value is dependent on the principal quantum number. It has positive values ranging from 0 to n-1. So when L equals 0, it will have s orbitals and has only 1 for each energy level. And when L equals 1, it will have p orbitals, which has 3 of these per energy level. And if L equals 2, we are describing d orbitals, 5 of these per energy level. Then if L equals 3, we get f orbitals, which has 7 per energy level. Third, we have the magnetic quantum number, or m sub L, which is the total number of orbitals in a subshell and the specific orbital for a particular set. Its value ranges from negative L to L. For example, if L is 2, then its values can be negative 2, negative 1, 0, 1, and 2. The last number is the spin quantum number, or m sub S. It tells which direction the electrons is spinning. There are 2 directions, spin up and spin down.
So before moving on any further, I would like to talk about the term degenerate used in quantum mechanics to mean of equal energy level. To understand this concept better, we would have to go back to the topic of energy levels in an atom. As we know it, there are orbitals in each of the energy level, right? Well, we can link that to the topic of degenerate energy to understand it better. For example, we can say that the orbitals in 2p are degenerate. This means that the 2px, the 2py, and the 2pc orbitals all are equal in energy. It must also be noted that the number of different states having equal energy level is called the degree of degeneracy, or just simply degeneracy. For example, we can say that the degeneracy of p orbitals is 3, the degeneracy of d orbitals is 5, while that of the f orbital is 7. Here would be a very simple diagram that kind of summarizes what I have said earlier about the degeneracy, degenerate energy, and the orbitals in general.
Imagine the surface of a pond and picture yourself simultaneously touching two different points of it. Well, ripples would radiate outward from each touch, eventually colliding and creating an intricate pattern. This phenomenon, where waves overlap and combine, is akin to the idea of superposition. In the world of quantum science, fascinating objects like electrons and photons also exhibit wave-like properties that allow them to combine and form what we call superposed states. To illustrate the profound implications of superposition, let us journey into a renowned thought experiment, Schrödinger cat. Schrödinger's cat is a thought experiment proposed by Erwin Schrödinger in 1935, and it is used to describe the weirdness of the quantum system that could be a problem when applied to the macroscopic scale object, and in this case, a cat. According to Copenhagen's interpretation, the particles could exist simultaneously in multiple states, and once it is measured and observed, then it will exist in one state or the other, which doesn't really seem to match with the reality. The imaginary experiment states that a cat is sealed inside a box with some radioactive substance. Controlling a vial of poison, there is 50% chance of the substance to decay, and if so, the Geiger counter will be triggered and then cause the poison to be released and then kill the cat. So when the box is closed, it is impossible to tell if the substance is triggered or not. The observer cannot tell if the cat is dead or alive, but all we know is that the probability of the cat being in either stage is mathematically a half. In quantum system, Schrödinger explains based on Copenhagen's interpretation that the cat exists in superposition stage where it is both dead and alive at the same time. But on the other hand, once the box is opened and the cat is being observed, all the possibility will collapse into one answer, and hence the observer sees the cat in the definite state. In relative macroscopic terms, it is illogical that before opening the box, the cat is in both states of being dead and alive, and the final definite state is dependent on the observation. Well, the problem is that it has no limit to the probabilistic effects on things being in the superposition state. Does the cat count as the observer of whether the atom will decay or not? Well, the way the cat behaves like this is called a quantum indeterminacy or the observer's paradox.
So let's talk about the electromagnetic waves. Electromagnetic waves are waves that can travel to the emptiness of space at the speed of light. It can travel to the airs, the solid objects, and even a space. And this is how the astronauts on the spacewalk use radios to communicate. Electromagnetic waves consist of amplitudes, which is the vertical distance from the midline of the wave to the peak or trough. The wavelength, which is the distance between the identical points on successive wave, and a frequency, which is the number of waves that pass through a particle point in 1 second. Electromagnetic waves propagate at the speed of light, which is 3 times 10 to the power of 8 meters per second. This speed is equal to the wavelength of the wave times the frequency. So when the wavelength decreases, the frequency of the wave increases. So from here, you may wonder why electromagnetic waves are different from other waves in nature, like an ocean wave that has both a crease and a trough. The answer to this question is because electromagnetic waves are composed of electric and magnetic field. It is formed with an electric field, which is shown in the red arrows or y-axis, coupled with a magnetic field, which is shown in the blue arrows. They are perpendicular to each other and to the direction of the wave. So when the electric field is changing, it will create a change in magnetic field, and on the other hand, the change in magnetic field will also create a change in electric field. Therefore, the electric field is equal to the speed of light times the strength of the magnetic field. The electromagnetic waves can be created by any types of sharp particles, and the sharp particles often has an electric field around it, and the moving sharp particles can create the magnetic field. For example, in the hydrogen atoms, there's an excited electrons in the third energy level, and when the electrons drop from the third energy level to the second energy level or lower than that, and also every time that it goes from a high energy level to a low energy level, it can emit an electromagnetic wave, and sometimes it can emit a photon of light. And the formula for the energies of photons is equal to negative 2.18 items 19 to the power of negative 18 joules times 1 over n final square minus 1 over n initial square, where n is the energy level of the electrons. So in summary, when an electron absorbs a photons, it can jump from a low energy state to a high energy state. But when it falls from a high energy state to a low energy state, it can release a photons in the form of an electromagnetic wave. Moreover, when electrons are oscillating with a metals, it can also emit electromagnetic waves even when they are heated. So back to some basic example of electromagnetic waves. When you listen to the radio, watch TV, or even a cooking dinner in a microwave, you all are using an electromagnetic wave. Radio wave, television wave, and a microwave are all types of electromagnetic waves, and the only differ from each other in is wavelength. And the electromagnetic spectrums contain of this wave, categorized by the wavelength or frequency, and include radio wave, microwave, infrared, visible lights, ultraviolet, X-ray, and gamma rays. Within electromagnetic spectrums vary in size from really long radio wave like the size of building to a really short gamma rays that are smaller than the size of the nucleus of an atom. Yet their size can be related to the energies, and this visible part of the electromagnetic spectrums consists of the color that we see in a rainbow, from red and orange to blue and purple. So for the easy to understand, let's imagine the
white light as a beam of light that flying from the sky, and as it reached the floor, it is separated into 7 people with different light colors of skins. In this case, the floor represents the denser medium that the white light had passed through, which caused the dispersions, and the 7 colors represent the colors of spectrums that appears in the rainbow after the refraction. So next we'll introduce you to the new topics, which is Planck quantum theory. We will talk about Max Planck work and how his work became the fundamental role in the development of quantum chemistry. So at the time, Planck was checking out this thing called the blackbody radiations, which is basically when an object emits electromagnetic radiations because it's all heated up. And the problem was that, according to old physics at that time, the radiation just get crazily intense as the frequency get really low, but his experience said otherwise. So Planck came up with this wide idea that he said energies come in this little bundle called quanta. It means energies can only be given off or taken in as these discrete packets, not in a smooth continuous way, and therefore it was basically a total game changer. This idea has laid the foundations for understanding the behavior of electrons in atoms and molecules.
Not that Planck, bro.
Let's get into detail about the beam constantly Planck constant. Beam constant represents the smallest possible units of energies that can be changed or emitted in the form of electromagnetic radiations. The formula describes the energies of a photon, which is a particle of light, in relationship to its frequency. The equation is given by E equals hv, where E is the energies of a photon, h is the Planck constant, which is the fundamental constant of nature. This equation explains the fundamental relationships between energies and frequency in the quantum world.
The photoelectric effect, first observed by Albert Einstein in 1905, revolutionized our understanding of light and laid to the groundwork for the development of quantum theory. It describes the phenomenon where light, composed of the packets of energy called photons, interacts with matter, particularly metal surfaces, and causes the emission of electrons. So when the light irradiates the metal plate, the electrons will move away. They get ejected in response to incident light, which can be detected when it interacts with the positively charged wire or plate sensor. The contradiction was that light's capacity to expel an electron depended only on its frequency as opposed to its intensity. Increasing the intensity only increases the number of electrons ejected if the threshold frequency has been reached. So if the frequency is increased, the ejected electrons will have a higher velocity as well as the kinetic energy they emit. The conclusion seems a bit strange. Albert Einstein solved the problem by extending the concept developed by Max Planck, who proposed that the energy is not continuous. In fact, it is quantized. This made Einstein think that light might be quantized as well, which he called it photons, and the particle of light, which actually makes sense. It only takes a photon with a very low intensity of beam, above a threshold frequency, to be able to make the electron ejected. On the other hand, if a photon cannot reach minimum energy, or it has a very low frequency, no matter how many photons strike the metal, no electrons will be ejected. Well, the photoelectric effect proves that light has a wave-particle duality. It shows that light consists of discrete bundles of energy known as protons. This meant that light was not made of waves or particles, but actually of both. This is the first discovery in series that brought about the quantum revolution. It completely changes the landscape of physics and how we build the universe.
One application of quantum chemistry can be the tunneling electron microscopes. They are a type of microscope that uses quantum tunneling to image surfaces of materials with atomic precision. It is a technique for obtaining high-resolution images of specimens, used in biomedical researchers to investigate the detailed structures of tissues and cell organelles. These images provide key information on the structural basis of the cell function and of cell diseases. The microscope is able to see some of the smallest details by using electrons rather than light as a source of illumination. Because electrons have a wavelength up to 100,000 times shorter than that of visible light, electron microscopes have a much better resolution than the traditional ones. So, how does it work? Due to these electrons having wave-like properties, the waves don't come to a stop when they hit a barrier. If the barrier is thin enough, the probability function may extend into the next regions through the barrier. When an electron moves through the barrier in this fashion, it is called tunneling. These electron microscopes make use of this effect by scanning a very short metal wire tip over a surface, bringing the tip up close and applying electrical voltage to it. We can register variations into the tunneling current and process the obtained information to create a high-quality image at an extremely small scale down to resolving atoms one by one.